Welcome, everyone. I'm Ryan Fox, developer advocate here at Algorand, and I want to welcome everyone to another edition of our Algorand Developer Office Hours. Today, I'm joined by my colleague, Jason Weathersby, and he's going to be introducing the newly released updates to TEAL version 3, what those OpCodes are, what they do, and how you can make these updates in your code going forward. So with that, Jason, welcome.
What we're going to be covering today is the updates that we're rolling out currently in TEAL version 3 for smart contracts. And I will also briefly touch on what we're working on for TEAL 4, which should be available in a couple months. So we're making many updates to the smart contracts on Algorand, in addition to offline smart contracts. So to get started with, I'm going to do a quick review. If you haven't seen any of our talks on smart contracts, there's a link to one in here that goes into detail on smart contracts. But as a base level set for what's new, I'm going to go through some of the changes. So to start with, Algorand has two types of smart contracts. We have what we call stateless and stateful contracts. These are both layer 1 smart contracts. And we'll dig into what each one of those does in just a moment, but those are the two primary ones that we have on-chain, right? Additionally, we're developing off-chain smart contracts that we'll discuss at a future day. Well, these two contracts, the stateless contracts, are primarily used to approve spending transactions and can be used for things like escrow accounts and delegating your signature authority, things like that. Stateful contracts are what we think of as applications. This is TEAL code that lives on the chain and responds to different transactions that are submitted to that particular application. And we'll dig into a lot of detail on these as well. These two types of contracts are also combinable using atomic transfers with Algorand with virtually every one of our layer 1 features, which includes Algorand assets, which you can use for creating fungible or non-fungible tokens. And you can combine both stateful and stateless contracts together in a single application. And atomic transfers obviously allow up to 16 transactions to be submitted at once. If any one of the transactions fails, they all fail. These smart contracts are written in a language called TEAL. The acronym stands for Transaction Execution and Approval Language. TEAL can be written by hand, and which you're going to see a lot of that today, but also can be compiled using a PyTeal enabled compiler that we have. So you can write your smart contracts in Python and compile them to TEAL using the compiler, the PyTeal compiler. In addition, if you're not into writing TEAL code, or you don't want to get the nuts and bolts of writing a smart contract, you can use something like the Reach framework, which Reach is a really great tool that is a framework that allows you to focus on the business logic. You write all the business logic in a JavaScript-like language. You compile your program, and it generates all the smart contracts for the Algorand network needed below. In addition, it also formally verifies those contracts as well, mathematically. So it's a really nice framework for just building applications on Algorand. All right, I'm going to break, just as a quick review, I'm going to break down the different types of contracts and how they're used. For a stateless contract, you can use it in one of two ways, and this is the first of those two ways. You can take some TEAL code, you compile that TEAL code, and it would generate an Algorand address, just like any other address on Algorand, whether it be a standard address, a multi-sig address. Now, this is called a contract address. All right, and when you compile this logic, it produces this account that any other account in the system can fund. They can send algos to it, they can send assets to it, but anybody in the system can send to this account. But the only way things leave that account is if the logic is verified, and the TEAL logic is verified when the transaction is submitted. So, for example, if I create an escrow account, I load it up with assets, maybe my fungible tokens or some algos, and then someone wants to take from that particular escrow. They submit a transaction where the from address is the contract account, and then wherever address they want to send it to. When that transaction is submitted, the logic is evaluated in the smart contract. If it's approved, the contract will push out and allow the transaction to go through it. If it's not approved, then the transaction will be rejected. So that's typically how we use a stateless contract as an escrow, or we call it contract address account. All right, another way that stateless contracts can be used is by using in a delegated fashion. And what this means is you have this piece of TEAL code, people sign, some user account signs that TEAL logic, And that logic is then later used to sign a transaction. And what this would be used for, let's say you have a mortgage and you want the mortgage company to be able to withdraw a certain amount of money from your account once a month. You can actually compose that logic and then sign that logic. And then the mortgage company can then once a month submit a transaction on your behalf, taking funds from your account to their account. And the TEAL logic is evaluated at the time the transaction is evaluated. Same way. The only difference is you're signing the logic as opposed to letting the logic sign the transaction, as we saw in the escrow account. So that's another way. Those are the two primary ways stateless contracts are used. Okay, and that's those. We've had those for quite some time. But what was the newer one this past summer is we came out with stateful contracts, and they function a little bit differently. Stateful contracts are composed of two TEAL programs, and I'll explain the difference of the two in a minute. But these two TEAL programs live on the chain, just like an ASA, what we call an ASA in Algorand, which is an asset. You create it, and you get an application, an asset ID when you create an asset. When you create a stateful smart contract, you get an application ID for that particular smart contract. This contract can be, and then to initiate communication with that transaction, you communicate it with a set of transactions. And the two TEAL programs, depending on the transaction type, one of the two TEAL programs will fire and it will execute its logic and do whatever it does. Now, a couple things that it has access to is it has a global state section that allows up to 64 key value pairs to be stored in global state for that particular contract. Now, in addition to that, and that's without any user opting into the smart contract. You also have access to modify users' local state. And what that means is if Bob opts into this stateful smart contract, then the contract can actually write up to 16 key value pairs into Bob's local state. And in the ledger, it's actually stored under their account. And it's just like their algos would be stored or their ASAs would be stored. So those are the two things that's the primary way that stateful smart contracts function. They manipulate state. Now, I'll talk about the two programs on the next slide, but as I said earlier, you communicate with the stateful smart contract with what we call an application transaction. Well, there's 6 types of those transactions, and these are the ones that are listed here. You have the no-op application transaction, which just is the standard transaction call to any stateful smart contract. And this is typically where you'll implement your logic. Most of your logic is in a no-op application transaction call. Then you have the opt-in call transaction type. Anyone who wants to opt into your stateful smart contract will use that transaction type. Then we have delete and update transaction types, which are unlike smart contracts on other systems. The smart contract on Algorand can actually be updated and or deleted. Now, if you don't want that to be the case, you actually have to put code in a smart contract to prevent that from occurring. And then finally, there's 2 ways to exit a stateful smart contract. One is to do it the graceful way. You issue a closeout application transaction. When all the top 5 of those go to what we call the approval program. That's the primary code logic for your entire application. Then if that particular closeout operation, because it's going to that approval program, can fail, that would leave the user stuck in a smart contract they maybe don't necessarily want to be stuck in. So the non-graceful way is you can issue a clear transaction, and it will call the clear program, and whether the clear program is successful or not, it will still clear the user out of the stateful smart contract and free up their local storage. And the reason anybody would want to do either one of those is anytime you opt into a stateful smart contract, your minimum balance goes up based on the amount of storage that's used by the smart contract. So these are the 6 types of, and this is where we're going to spend most of our time today, because this is where a lot of the TEAL code 3 changes are made. I'm going to be showcasing how I run several of these and show some examples of digging through the new OpCodes. So these are the 6 different transaction types that the system supports, and those are the 2 programs. And so we've got the approval program for most of your logic and the clear program for, typically in clear program, you're going to want to clean up the user's local state. So if you're storing some variables in there, you might want to delete those. You may want to modify some of your global state, that type of thing. But as a good smart contract writer, you should also make sure that the closeout in the graceful manner works in a proper fashion. Okay. So moving on. Bob, if you want, here's a link to a full talk that I give on this that goes through pretty much everything about smart contracts, and I walk through a bunch of TEAL code, explaining some of the basic TEAL opcodes. And so if you haven't seen that, make sure you do go see that. All right, so from a runtime architecture review, I want to explain this as how things are different between the two systems, between stateful and stateless contracts. And then we'll jump into the TEAL 3 updates. First thing is, in a stateless smart contract, you have a anytime you submit a transaction that involves a stateless contract, that means if you're going to have an escrow and this escrow wants to pay Bob, well, you're going to submit a transaction from the escrow to Bob. You supply the TEAL program and a set of arguments associated for that per transaction. The node itself has a stack engine. TEAL processes the smart contracts using a stack engine. We'll get into details on that in just a second. And TEAL is going to return either a 1 or 0. It's either going to fail or it's going to succeed. And the way it determines that is if any positive value is left on the top of the stack, one value, it will return true and the transaction will go through. If a 0 is left on the stack or more than one value is left on the stack, the transaction will fail. The only caveat to that is if you use the return opcode, it just takes the last value on the top of the stack and returns either true or false based on that value. All right, so the stack has access to transaction properties that are associated with the transaction and a set of global variables. The transaction properties are not just the transaction that's submitted, because this particular transaction may be being submitted as a group transaction. So I may have a call from a stateless contract to Bob, but I may also tie that with a payment transaction from Bob to the escrow. And so I can interrogate inside the smart contract all the transaction properties for either transaction. That's why I have the S on the end of that. So that's the basic runtime architecture. Okay, and then you can read and write. We do also, in addition, you can read and write to some scratch space inside the stack engine as well. And I'll show a little bit of that as well. Okay, on a stateful smart contract, the runtime architecture is a little bit different. The smart contract actually lives on the chain. So you don't have to supply the TEAL code associated with the transaction. You just call the application ID. In addition to that, here's a set of values that you can actually pass per transaction. You can pass what we call the application array. That's up to 2 foreign apps that can be passed into the smart contract so it can go read their global state. So you can think of this as if I have a smart contract A living out there with some master values that smart contract B wants to reference. Then I would pass smart contract A into an application array if I want to interrogate the values associated with that other application. The accounts array allows me to interrogate not only the sender's account, but up to 4 additional accounts. And what I can look for is their ASA balance, their algo balance, or any of their local storage values for any smart contract in the system. So, and by the way, these calls can be changed per transaction. So you can load up one set of accounts for the first transaction, another 4 accounts for the second transaction, and so on. So you can when you want to interrogate an account, then you want to absolutely pass it in the accounts array when you submit the transaction to the stateful smart contract. Now, using the accounts array, I can also look up their asset balance. What if I want to know the configuration of that asset? The only way to do that is you have to pass that asset ID in the assets array. So I may say, okay, I want this to be able to interrogate the configuration of asset B. Then I would pass asset B in the assets array, and I can interrogate the actual configuration of that. And that includes things like its URL, metadata, total supply, unit name, those type of things. And then additionally, you can pass a set of arguments to the smart contract as well. So when you submit these, then this will fire your TEAL program up, and it'll initiate your TEAL program, and it'll process the TEAL program one line at a time in the stack engine and read and give you access to reading and writing global local state for each user, global state once for the one copy of the global state for the stateful smart contract. In addition, you also can read the transaction properties just like stateless. And then you have a few more global variables that you have access to, like you can check the time of the latest block on the blockchain. All right, so that's the runtime architecture for stateful TEAL. Okay, so now I'll step into the TEAL 3 updates. TEAL 3 is the primary thing that we're adding is we built a lot of improvements for tool builders in TEAL 3, and so I'll be covering some of those and explaining what those mean, but primarily we've added some additional transaction properties, and we have a whole set of new opcodes that I want to explain, and then we have some way of dealing with group transactions that's an improvement that allows you to do some indirection and allow to not have to hard code so many things in the actual smart contract. So getting that started, I want to first off just show how TEAL processes a simple stack, a simple TEAL program using the stack. All right, so I have this TEAL program. This essentially says is I want to know if the transaction amount is greater than 1,000 microalgos. So I use the TXN opcode, and then I pull out the property amount. And then I use the pseudo operator int, and I push 1,000 on the stack. And then I check to see, I use the greater than or equal to operator to see if it's actually greater than or equal to that. What it does from a standpoint of how the stack engine processes, the first command, what it does is it puts the transaction amount on the top of the stack. Then the next command uses the int pseudo operator to push 1,000, an integer, onto the top of the stack, and it drives the transaction amount down into the stack. And then the next command, what it does, the greater than or equal to opcode actually pops two values off the stack. It treats those as the parameters to it and returns either 0 or 1, depending on if the transaction amount is greater than or equal to 1,000. So in this case, it would push a 1 on top of the stack. And so every opcode functions this way. It takes a set of parameters and it pops a certain amount of values off the stack and puts a value on the stack. And those are all defined in our opcode documentation. So if you look here, this is the opcode documentation for greater than or equal to. So we notice we're popping A and B off the stack, and it pushes a uint 64 onto the stack, which is going to be 0 or 1. And this is A. You can see the order matters when you're doing TEAL programs. So in this particular case, this amount would be A, and B would be the 1,000 microalgos. And let me bounce out of this for a second. In our developer docs, in the reference, we have opcodes. This is where they're all defined, and you can just look at any one of them and see the opcodes there. All right, so getting back to it. That's just a simple way the stack engine works. Let's move along. Okay, a couple things about versioning. Depending on the version of TEAL that you're implementing, you specify at the top of the program. In the case of TEAL version 2, you just put Pragma version 2 at the top. What that does is it restricts the opcode sets that you can actually work with. And in order to take advantage of TEAL version 3 opcodes, you need to supply Pragma version 3 at the top. So that's just for note for thought. If you do not specify any Pragma version at the top, it will assume TEAL version 1, which is the most restricted set of functions that we started with. So we're at TEAL version 3 now. And like I said, we're actually in the process of working on TEAL 4. I'll give you a sneak peek of that at the end of this presentation as well. So moving along, as I told you earlier, sometimes you're going to want to read some other stateful smart contract from an existing smart contract. So the way you would do this is you would in this case, so let's say we have some global master value sitting here, and I want to derive some value in this stateful smart contract based on that global state of this smart contract. Well, when I call this stateful smart contract 1, what I'm going to do is I'm going to pass the master smart contract's ID to the transaction call. And then I can actually look up that global state value. And the way this would be done, I'll show that just in a second. I'm going to actually show you a demo of this. But one of the things that we allow now is we've added some additional transaction properties to support better interrogation of that applications array. So in this case, we've added, okay, there's a transaction property that allows you to look up the number of applications in the application array. In this case, I'm looking for, is it the transaction number of applications equal to 2? That's all I'm looking for. So if I pass 1 or 0 or more than 2, then this set of opcodes will actually return a 0. And then the last thing we have is another transaction property that allows me to actually interrogate the application ID and verify it's what I'm expecting. So I can look at transaction applications, that's the applications array, And then I can say, give me the first foreign app that's passed in. And then I can actually compare that to an ID and make sure it's the one I want. As a quick example of showcasing that, I'm gonna let me explain a little bit about my development environment so people understand what I'm doing here. All I have is a terminal, VS Code open. I have two terminals. One is I'm using to start and stop a private network. And this one is where I'm running some shell scripts and just do the goal commands to create and deploy the smart contracts. Here's my smart contracts, or the .teal files. The reason I do it this way is because when I'm doing debugging TEAL, what I want to do is make sure that I want to make sure that I get my contracts fully debugged before I put on an integration code on top of that, whether I want to use JavaScript, Java, Go, or whatever. So I typically write all of them in just using Go and TEAL, and then I deploy them, test them on a private network, and then I put my integration code on top of that. So it's just a two-step process for me. So, and this private network is nothing more than just a little shell script that fires up a private network, and you can look at, we have a tutorial on how to do that, and there's my network template. So let's go back to here. All right, so I'm gonna start the private network. Okay. All right, so now the first thing I want to do is I'm going to create this, use this shell script. And what this does is just this, assume this is just goal. I just got a different path for my goal. So this is goal app create. What that does is creates my smart contract application. And this will return an ID that I can reference to make calls to it. And I'm passing an approval program called master. And then this is where I'm specifying the amount of storage that should be used by the smart contract, global or local storage. And then there's my clear program, as I discussed earlier. And these two programs would be down here. Here's my master program. And you can see here, this is a key value. This is the value I'm setting it to, and I'm storing that in global state with that particular opcode. It's called app global put. All right, so let me just run that particular one real quick. Okay, so once that creates that, you noticed that when I did that, I'm also creating a secondary one. I'm going to dig into the code of that in just a second because we're not going to debug the master TEAL program. We're just looking at the secondary. But I have these two applications created. But since I've just started the network, this will be app ID 1 and this will be app ID 2. All right, so the way I debug that is I'm going to run this little script here, and I'm going to call. This is where I call the secondary TEAL program. This is the from account who's sending the transaction. And this is where I'm specifying I want app ID 1 in the applications array. And then I'm just using our TEAL debugger here. I just putting all this in a shell script. And I use the out to dump the transaction, and then use a dry run dump to format all the stuff I need for actual debugging. And by the way, the code for all this will be available. All right, so I'm going to debug. Let's see. Oh. All right, so now once I launch the debugger, I can click on, all I'm doing is, well, by the way, what this does is our debugger works with Chrome developer tools. So it gives you a URL that you can go to, or you can just click on any window and just type Chrome inspect, and it'll show up down here. So I can actually click the inspect. And this is my TEAL program for that secondary TEAL program, okay? So stepping through this code, I'm gonna just one line at a time go through it. Here's my stack, the one that you saw earlier. That's my stack. First thing I load on it is an integer of 0. And then next thing I'm gonna do is I'm gonna actually get the transaction property called application ID. Now you'll notice that it returns 2 because that's the second app ID. What this logic does is then compares those two, equal, it'll pop both of those values off the stack and return 1 or 0. In this case, it returns a 0 because the application ID is not equal to 0. The only time application ID will ever be equal to 0 is when when you're actually the first transaction actually create this stateful smart contract. So in this case, I'm doing what we call a B and Z, which currently in TEAL you can branch forward. You can only branch forward. It's not Turing complete language, so you can only branch forward. And we have 3 branching commands. We have B, B and Z, and BZ. B and Z checks the last value on the stack, and if it's a 1, then it will, or positive value, it will go to this label. If it's BZ, it looks for a 0 on the top of the stack and will go to that label. And the other one is just B. If you just use the B opcode, it just branches regardless of what's on the stack. So in this case, I'm looking to see if we're actually creating a smart contract. If we are creating a smart contract, that's bounced down to this label here. And you're going to see this piece of code in virtually every example I have. All right, so moving along. So the first thing I do is this is a new feature. Like I said, you can actually interrogate how many applications were passed in. And that particular command returns 1 because we passed in that one application ID when we called it. And I'm just verifying that it's if it's greater than that. And if it's greater than that, then I'm going to bounce to the failed command. In this case, it will not be greater than that, so we won't actually branch to the failed label. The next thing is I can actually interrogate the application ID by calling TXN applications 1. So if I do, that'll load 1 on the stack because that is the application that actually got passed in. This would be the ID of whatever you pass in. And I'm just verifying it's the one I expected, and it is. Now, this is how I read that global state from that other contract. First thing I put in, this is actually, this is the index into the application array. And you'll notice it's 0-based, but we're putting a 1 here because it's the first additional app in the application array. The application array actually has my current stateful smart contract in the 0th position. So I just put 1 here to say, give me the first additional one passed in. And then this is the key that I want to look up on that particular contract. And then I'm going to use the app global get ex command to actually go out, read that smart contract, and bring me back that value. So that's what this does. Now what it does, but it also takes, so it takes the index into the application array, the key, and it pops both those off and returns 2 values. It's going to return one value is going to be at the top of the stack. It's going to be a 1 or a 0, whether it's successful or not. If it's successful, the second value in the stack will be the actual value that it returned. So you'll see that says that we succeeded, and there's a saying the value is actually 5,000. So then I can, all I'm doing is comparing that it's actually 5,000 and what I expected it to be. And then I'm returning at the end of that particular piece of code. So I'm going to play that out. All right. So going back to my presentation, those are 2 new features that we have for TEAL 3. And then I want to talk a little bit about assets in the accounts array. Like I said earlier, anytime you have the accounts array, you can look up anything about that user associated in the ledger. You can look up their asset algo balance, look up their asset balance. You can also interrogate their local storage values for any contract in the system. The only time you would use the assets array is if you actually want to dig into the configuration of the particular asset. And we do have 2 new globals for getting the number of assets in there and the actual asset IDs, much like the other 2. Now I'm going to show you a demo. It's fairly similar to the last one, but it'll be slightly different because I'm going to show you how to look up the balances. So one thing I do is I stop and start the network after every time just because I want to make sure I get the same IDs, and it makes writing a script easier. So I'm going to create this assets demo. All right, so once that creates that, all this is doing is creating one asset that I'm going to be using in my test, and I'm creating it with a 1,000,000 count, and this is what I'm naming it, the unit name, and I'm no decimals. Then I'm creating my smart contract to actually check into to actually interrogate that particular asset as a demo. All right, so let me run the debug on that. All right. So I'm in this little piece of TEAL code. Looks very similar to the second one, the first one you saw. The difference will be down here how we check the balances. So if I look at this, this is the same code you saw before, so I won't bother explaining that. But new is we can actually look up the number of assets passed in. This says there was 1 asset passed in. I'm just verifying it is equal to 1 and doing the same branching that I talked about earlier. Now I'm going to actually dig up the asset ID. Since it was the first asset created in the system, it's asset ID 1, and I knew it was going to be that way because I stopped and started the network. All right, so I'm just comparing to see if those 2 are equal. Same thing. Now to get the if I want to get the configuration information for that, there's a couple things. You're going to use the asset params get opcode on line 25 here. But to get without, if I just want to get their balance or whether the asset's frozen or not for a particular account, the first thing I'll do is pass the first parameter will be an index into the accounts array. And this will be that 4 accounts that I told you about earlier and the sender. So it's really a total of 5 accounts. It's 0 based. So the first int 0 says, I want the sender. And then you pass the second command is the ID that you're looking for. This is the asset ID. In this case, it would be 1. And make this call asset holding get asset balance. That'll pop all of those values off the stack and push back the actual asset balance for that particular user. So if I step through the stack, looking at this, first thing that's loaded on the stack is the index into the accounts array. Second is the asset ID. And then we pop that call and it returns the asset balance returns 2 values. The top value is being whether it was successful or not, did it actually get the value? And the second one is the value that it's returning. So this is the asset balance saying that this particular user, the sender of this transaction, has 1 million of this particular asset. And then you can, I'm using a BZ here. And one thing I should have stated is when you do any of the branch commands, it's going to pop the value off the stack. So it pops that 1 off the stack, and that's left with my value. And I'm just comparing to see if they have more than 1,000 of this asset. And in this case, they will. Now, if I want to get the actual configuration information about that particular asset, what I'll do is give an index into the assets array. And in this case, it's 0 based. Again, the first asset in the asset array is going to have an index of 0. So that'll be that asset. And I'm going to call asset params get, and what the value I'm interested in returning is a unit name. There's a bunch of different parameter configuration properties you can look in the OpCodes document, and it'll show you which parameters you can actually put here. But if we just step through the debugger, load it in on there, and saying I want the first asset in the asset array, and I want to go out and get the asset unit name for it. And then you see it again, it returns 2 values, the top being whether it successfully found the configuration, and second value is the actual value of the value you're looking for. So in this case, I'm going to pop off that top value on the stack, and we'll be left with the actual unit name of the asset. And I'm doing a byte string compare of the 2. And that's pretty much it on that. So I'll just return out of that one. All right, so getting back to the presentation. All right, a couple other things have been added. One of the things that people typically do is explain to you that you can update or delete a stateful smart contract. Anyone can. So a lot of times people will put put logic in to prevent that from ever happening, or they will put logic in that says only the creator can update or delete the smart contract. The problem with that approach in previous versions of TEAL is we didn't have access to the creator address. So the first time you created the smart contract, we'd have to take the sender's address and store it off in global state, which you only get 64 key value pairs. So that was burning one of those immediately just to store the address of the creator. So now we have that as a global variable for any time a stateful smart contract runs. Another new option is when you configure the transaction, when you first do that submission, you specify a bunch of parameters associated with how much local and global states used. These are specified in uints and byte slices. And you can actually, now we have transaction properties that actually specify how much was being asked for. So think about this would be used in the creation of the stateful smart contract. Those values would not be available in any other time. The only time that you would see those values is when the contract was actually being created. So if you look at just as a quick, actually I'll skip that one because we're going to run it a little bit on time. I want to get into the opcodes. All right, so some new opcodes that we have, the assert opcode. What this opcode does is if the transaction, if the top of the stack has a 0 on it, it immediately fails and returns. So instead of having to do all that branching you saw in my previous examples, I can just put an assert command in there. Okay. The second, another opcode that we've added is called swap. Now, what this does is allows me to take the top 2 items on the stack and switch them. Okay. And if you look, for example, why would I want to do this? Well, typically, here's an example in TEAL version 2 of incrementing a global variable. So here's a byte key value name. So the name of the key value pair is total. And I want to go out and get it. And then I get a transaction amount. This is actually 2 transactions grouped together. So I'm getting the second transactions amount and I'm adding to that total. And you'll see I'm doing this store 1 here. All that does is store it in local scratch space. And the reason I'm having to do this is because the order of parameters matters. So when I put byte total, this is where I'm getting ready to store the value. I have to start with byte total and then have the value and then call the app global put. So you see these store and load were just there because I have no way of manipulating the stack. And the order, the parameters are in the stack. So with TEAL version 3, you can say TEAL, same piece of code as TEAL byte total, app global get, and then I get the amount, increment it, and then put byte total on the key name on it, and then I just swap that because the 2 values will be on the stack of the actual accumulated value and that. And all I hit swap, it switches those 2, and then I can make my call. Okay, I want to show a couple of these as we're going through them because I'm going to get into some of the bit operators as well. So let's look at, let me stop and start the network. All righty, so let me create opcodes.sh. This is just one big TEAL contract with all the new opcodes in it. So we can just look at them one at a time. And so now I'm going to debug it. All right, so let me go inspect that. So I'm going to, this is the same logic we saw before. I just use a breakpoint and play down to it. You'll notice that I have the assert command here. What it's looking for is going to take the top value, pop it off, and it'll return, if that's a 0, it'll return a failure at that point. The swap command, so look, if you look here, when I put the first value on the stack, then I put the second value on the stack, you'll notice this is the top of the stack now, and this is the bottom of the stack. When I do swap, you see what it does. It reverses that order. Okay, so that's the new swap command. I'm going to leave that up for a second. Okay, and then we'll get back into here. That's the swap opcode. Then we also have a new opcode called dig in. And what that does, what it allows you to do is 0-based, and it digs that far into the stack, makes a copy of that value, and pushes it to the top of the stack. So in this case, we have first, second, third, fourth. That's 4 values on the stack. If I do dig 3, it's going to go to the 4th value on the stack. Because of the order of the way the program is, this will be the lowest thing on the stack. And I'll show that in just a second. And then new to TEAL 3, we also have the ability to get and set a bit. Now, why does that matter? Obviously, doing bit mathematics is very nice, and we didn't have that capability in TEAL version 2. What we think about some of the ways you would use this is if you have 64 key value pairs, those values can be either 64 byte slices or unit 64s. So if I wanted to maximize my space, I could say, okay, I want to use a byte slice with 64 bytes, and that would result in essentially 512 bits per key. And if I multiply that times 64, I get over 32,000 bits that I can actually play with. And one way you may want to use that is, say you were doing a ticketing app and you wanted the bitmap to actually represent the seating arrangement inside of a stadium. That's one way you could do it. All right, so so we now have the ability to get and set a specific bit, and I'm going to show you an example of that. Okay, let me flip back to the debugger. All right, so first thing I'll show you is this dig command. So in this case, I'm pop. By the way, pop command just pops the last value off the stack. And you can see when I'm doing debugging, I'm always got my stack open, just looking at what values are on it. So first one, I put the first one, then the second one, then the third one, then the fourth one. Those are all on the stack. The 4th is sitting in the top of the stack spot. So when I dig 3, it's going to go 0, 1, 2, 3, and then make a copy of that and move that to the top of the stack. So it does that. Then I'm going to pop all of these values off the stack. All right, then as far as bit operators, I'll show you real quick how this works. I load int 235 on there. I want to read the 6th bit, so I specify the bit I want to read. This is the target. This is the bit I want to read, and then it's called get bit. And that value, since 235, the 6th bit is set, that'll return a 1. And then I'm just comparing it to 1 to make sure that's what I expected. All right, and then now I want to set a bit. I take that same 235, reload it on the stack, set the target bit that I want to change, and then I set the value that I want to set it to. So that should set that bit to 0, and it should pop all of those off the stack and return the resultant value. In this case, it'll return a 171, which is what I expected. So then that when I just compare that to make sure that's correct. Okay, so that's the getting set bit opcodes. We can also allow getting and setting of bytes. And this is nice because if you just want to set an individual byte or get an individual byte, same process is used. Hang on, and let me do that again. Same process is used here, and I'm just showing. Okay, this is I'll put the string on the stack, and then I want to get the third byte in that. So that'd be 0, 1, 2, 3. I want to get that T. So when I call get byte, it pops all that off the stack, returns a 116, which is the ASCII value of the T. All right, and I'm just comparing that's equal to that. If I want to check, if I want to set a byte, then I'm gonna you add the target, the byte to set, and the value you want to set it to. So in this case, I'm putting John, the string John, on the stack. And I'm interested in setting the second byte, which would be the H. And I'm going to change that H to a 105, which happens to be the ASCII equivalent of I. So I'm changing the word John to join. And so I load those 3 values on the stack and then call set byte. And you can see it's changed. And then I just compared the 2 to make sure they're equal. Okay. Next thing, we now have a conditional operator called select. And what select allows you to do is conditionally load 1 of 2 values onto the top of the stack. So what it does is it checks the current top of the stack, and if it's anything but 0, it'll take the very next item on the stack and move it to the top. If it's 0, it'll take the second element on the stack, push it to the top. And I'll show an example of that in a minute. We also have push int and push byte opcodes. These are primarily used for tool builders for increasing the performance of pushing integers and byte slices on the stack. You feel free to use those. And then and also here's another key new feature that people have asked for is you can see in this particular example, I can get the balance of the sender just by indexing into the accounts array and then calling the balance opcode. Sometimes if you're submitting a transaction, one of the most frustrating things to do is submit a transaction and fail the transaction because your minimum balance, the transaction would drop you below the minimum balance. We've added and the minimum balance changes for every account depending on what they've opted into. If you opt into an asset, your minimum balance is going to go up. If you opt into a Stateful smart contract, the minimum balance is going to go up, and it will go up determined by a calculation on how much storage is used in that Stateful smart contract. So it's sometimes difficult for you to calculate. If you use the min balance opcode, it'll actually do that check for you, so you don't have to worry about that. And so this is essentially this particular one is I was just looking at a spending application, subtracting the fee, the 2 fees associated with 2 transactions, and verifying I was over the minimum balance. All right, and then we have something now called relative transactions. And what I mean by that is typically when you're manipulating smart contracts, you're gonna use, group transactions, you're gonna use the GTNX opcode or the GTNXA opcode. The GTNX opcode just says, I want transaction X is property value. So if you look here in the first line on this one, it's GTNX1 amount. So I'm saying, give me the second transaction's amount. GTNX0 would be the first amount, the first transaction in a group's amount. So this is all I'm doing is using GTXN to look that amount up. If I want access to any of the array elements, and by that, the application array, the arguments array, the assets array, and the accounts array, then I would use GTNXA and then specify the particular transaction number and then the property I was interested in getting. So for example, if I wanted application args, I would go GTNXA application args. I would say GTNXA1 application args 0. Now we have 2 new opcodes that allow you to not hard code this one value. So essentially what you do is it reads the top value of the stack, and that uses that as an index into the actual transaction group. So I can actually make that more dynamic. So in TEAL version 3 here, I'm looking at the current transactions group index. That's what number in a group am I of up to 16 different transactions. It'll give me that number, and then I may add 1 to it and then return. And this would say, go out and get that latest transaction, that transaction I'm pointing to is amount. And it's pulling that instead of hard coding that 1, it's actually pulling that value off the stack. And the same is true with using, and this is called GTNXS. And then we also have GTXNSA, which is the same as GTNXA, except you're using that, instead of hard coding the value there, you're loading it from the stack. So it's basically using relative indirection. You could do a lot of nice things in code with that. Okay, so as a little bit of a wrap up, we have a couple things that are coming in TEAL 4, and this will be out in a couple months. And in fact, some of these almost made it into TEAL 3, but they didn't quite make it. But some of the things we're looking at coming in TEAL 4 is we're going to be adding functions to TEAL, so which will allow you to customize, write your own functions, and then have TEAL call those and jump where they'll jump to that function and then come back to where the code's at when you did that, and allow you to create some looping instead of branching just directly forward. And another thing too is every opcode in TEAL has an opcode cost. These are all calculated statically, and your program has to stay below certain minimums that are laid out in the reference documentation. If you write this large program, maybe you have a lot of conditional logic that doesn't execute at all. That means you're still restricted. So using we're now in TEAL 4, we'll be supplying dynamic execution costs, which means it won't calculate your opcode cost till the program actually runs. So then you can add a lot more code as long as your branching takes care of covering the cost of that. And then in speaking of costs, we have size limits on all TEAL code that we're actually revising all of those limits. Hopefully we'll see some increases where you can write larger TEAL programs. So that's a sneak peek of and that should be here in a couple months. I know the work's well underway on this. All right, so that's the sneak peek. Now, a couple things to keep in mind when you're writing smart contracts. Here's a couple of, this is a boilerplate approval program. We have an example stateless contract. If you want to write a stateless contract, but the guidelines is probably the most important thing to look at to protect your accounts. You don't want to, everything you saw today is just documentation type examples, not meant for production because there's no checks in it. So you want to make sure that you adhere to the safety checks so you don't lose money. And then we obviously have size limitations and all opcode cost limits. There's a link to how that's all calculated and what your limits are for stateful contracts or stateless contracts. All right, so there's several more examples in this group. You can pull them all down. There's an example of every opcode that you saw today in this particular GitHub location. You can pull it down, and if you want to take a picture of that, go ahead and grab a picture of it before I leave it. And then finally, we always put these up. Join our Discord channel, please, and we can continue discussions there. We have the developer portal. We're creating logins for the developer portal. If you want to become a member of the developer portal, feel free to. Not necessary. You can still read the docs without it. We have the forums, and then obviously our GitHub, and sign up for future office hours.